Right. Any questions while we are logging in? We'll go ahead and share my screen.
Dr. Russell, did you ask us if we had any questions?
Mm-hmm.
So last night we were kind of like talking, and as a class collectively, we wanted to ask you if you felt like it was okay to move the test back for Friday. We just need a little bit more time to review the concepts and get everything down. Like, it's not that it's like super hard. We just need a little bit more time. So we just wanted to ask you if like you feel like we can move the test back and see what date you want to move it back, if you would.
I'll consider it.
Okay, thank you.
Mm-hmm. Yeah, I'll think about it. I'll see where we are after today. I don't want to push it back too far, but I'll see where we are after today.
I have a question.
Yeah, go ahead.
So how would the test be given? Like, is it multiple choice? Are we like printing something out, writing it, turning it back in, or how would it be?
No, the exam is going to be, so we're going to take 6 tests and they're all going to be posted on Blackboard. So you'll have some multiple choice and then you'll have some file submission questions where you write the answer out and then upload it.
Okay, thank you.
Yep. All right. Any other questions? All right. So today we're gonna start with Allelic Bromination. Come on, man. What's today? 25th. Man. So we're going to start with Allelic Bromination, and this is, again, one of our methods that we discussed the other day regarding synthesis of alkyl halides, right? So the synthesis and application of alkyl halides, right? So that's the kind of the umbrella we're working under. So we're going to talk about this first method of Allelic Bromination, all right? And so I want to introduce it a little bit, and I want to work a few examples that'll help us to understand like the idea of the concept a little more. So first of all, it is a radical reaction, right? If you remember radicals from organic 1, right? So 1 electron process, and it follows what we call a mechanism is like a chain reaction. So you have initiation, then you have propagation, finger stick to the screen, and then you have termination. How many of you remember that? Anybody? From part 1?
Yeah, I remember it.
All right. So initiation, propagation, termination. Those are the 3 steps in any radical mechanism. And let me review that real quick. Let me review that right quick because let's say if you have CH4, right? And you wanted to do a halogenation on it. Right, someone said we get CH3Br plus HBr as the product. Right, the first step will be the initiation step. Where bromine is homolytically cleaved by light, right? You break the bromine-bromine bond, and then you get two bromine radicals. Right? And then in propagation, the radical that you made in initiation is it's going to go into, I'm going to write these hydrogens out. It's going to go and start attacking hydrogens on that methane. Right? And it's going to remove them through a process called abstraction. Right, so you're gonna cleave this bond, extend it some. Right, you're gonna cleave this bond like so. Everything here is homolytic, one electron. If you remember that from part one, homolytic means when you break a bond, both atoms get one electron. Heterolytic, you break it and one atom takes both electrons. So here, you homolytically cleave the CH bond with a bromine, and then so you end up with HBr, and then a new radical, a CH3 radical. Right, and then in termination, this is what I care about. Right, I want to terminate that. So in the termination step, I have Br, bromine radical. And then the CH3 radical that are going to combine homogenically. To give me my product. All right, anybody remember that from part one?
Yes.
Good. So that's the concept that we're going to be reinforcing. Right. So let me refresh your memory more from part one. And we're going to start out the exercise with some examples right here, right? So you remember, if hopefully you remember when we talked about, we did resonance. There were 4 patterns. We have allelic cation, allelic anion, an allelic radical, and we had a 2-atom unit where the charges were adjacent to one another, right? So an allelic radical, this is an example of one. It's allelic because of the location of that alkene relative to the radical. So all that term allelic simply means is that it's adjacent to an alkene, right? So the radical right here is adjacent to an alkene. How would I rearrange that through resonance? Anybody? Where would I start? This is, and the reason I'm doing this first is because this is really one of the key concepts in understanding the process of allylic bromination.
Could you make the carbon that's on the outside of the, was this a pentagon? Could you make it a double bond?
Yes, but how? Right, through, we're talking about resonance now. This is something that we should all be familiar with from part one, right? Resonance is rearranging bonds and electrons. You know, you can move electrons, but they have to be oriented a certain way.
So would you have to move the first double bond like over? Would you have to move that one first?
Yeah, but we're going to move it in such a way, right, where if it's again, if it's a radical, everything is one electron. So the way that we do that, you're right. Right, so that would be the resonance form. Right, well, now we take this one electron from the double bond and then one electron from the radical to make a new double bond here. Right, that's what we see over here. And then the other electron in the double bond ends up on this carbon right here, which is what we see here. The reason for that is because in order to do resonance, you got to have a certain a pattern. There has to be a donor and an acceptor adjacent to one another. So in this case, we'll say the donor is going to be the radical and the acceptor is the pi bond. I mean, how many of you remember what a donor and acceptor is? We're talking about donors, now we're talking about electron donors. Somebody give me another example of a donor.
Acid.
Electron donor. You're right in the sense that an acid is a proton donor, but an electron donor.
Is it a base?
Yeah, in a sense. Well, but I'm not speaking in general terms. I'm just speaking in terms of resonance. Like what would be considered a donor? Could a pi bond be a donor?
Like a cation or something?
In a long pi bonds and lone pairs. Do y'all remember that from part one? Lone pairs and pi bonds are donors. Cations and pi bonds are acceptors. Yeah. We got to do some jogging, some refreshing. But that's all right. Let's look at the next example. It's going to click eventually. All right. So again, what you're looking for here is that pattern. And you can see it. All allylic systems can do resonance because of the proximity of the donor and the acceptor, right? The allylic radical is set up perfectly for resonance because all you're doing is sharing electrons over those three atoms. So how would I rearrange that by resonance?
You move the double bond over to the right and then the electron over to the left.
So it's the same way I did above, am I right? So I'm gonna do that. That's gonna make a new pi bond right here. Yellow is bad, sorry. All right, that's gonna make a new pi bond here. And then what about the last electron, the second electron in the pi bond? Where's that going?
To the left.
Is it going here on that atom?
Yes.
Yeah, it's always going to be only these three atoms participate where the donor and acceptor are, right? All right, so now my new resonance form is going to, that pink is not good, hold up. It's too black. The new resonance form is going to be here with the double bond here and a radical here. All right. Now, oh, let me put this double bond back because I didn't touch that. Can I do it again? Do you see the same pattern again? Right here?
Yes.
Yeah. So I can do it again because I have the same allelic pattern. Right, so I'm gonna push that there, here, and then this sucks. Sorry, here, right? So then I have another resonance form. And again, this can keep going for as long as I have donors and acceptors until I get to the point where I can only go in reverse. So I'm gonna put this electron here and then put that pi bond there. So that radical had 2 resonance forms because, well, 3 total because it had a donor and 2 acceptors. So that's a kind of a little rule of thumb that I usually teach in part 1, which is that if you add up the number of donors and acceptors, it'll give you an approximate number of, or an approximate idea of how many resonance forms you're going to make. All right, what about this one here? What do you think? Can you see the pattern, first of all?
Yes.
Mhm. So you can do, you can rearrange that through resonance. And the reason I'm talking about resonance is for 2 reasons. Number one, when you make the allelic radical in allelic bromination, a lot of times it's going to rearrange and give you a resonance form. So you actually end up getting more products than it initially looks like you're going to get. That's the one reason. The other reason is if you can do resonance, it ends up lowering the energy of whatever system you're working with, right? So again, anytime you're doing chemistry, the lower energy pathway, or if you're able to lower or decrease the energy, that's stable. That's a stabilizing effect. All right. So what would you do here?
So the double bond's gonna move to the right.
It's going to shift, right? Just like we've seen
Yeah.
in the other 2 examples. So we'll have that. And the double bond is going to end up here, and I have an electron here. Let me put that back inside the ring. That might confuse somebody. All right, and then I still have this aromatic system back here. Can I do resonance here? Do you see the pattern?
It's like flipping the double bond from the left to the right.
Yeah, I can shift that. Now, under normal circumstances, I would say don't touch the aromatic ring because it's very difficult to interact with those double bonds in that ring because of how stable it is. But for this case, for the case of the exercise, we're gonna do it. All right, so I'm gonna do this. That's coming there. That's coming there. Where those arrows end up, that's gonna end up being a pi bond. Right. So on the other side of the resonance arrow, this is what I'm gonna get. Right, so that's still there. That's there. And then I need to put one more arrow in here in that pi bond to show that where that last electron is going. Right. Now, what do you notice here? Right. You can see you got this pattern it keeps repeating. Right. You got another allelic radical right here that you can also do the same thing with. So you can do it multiple times because you have, again, multiple donors and acceptors. Any questions about that? This is all review from organic 1.
Yeah, what's the purpose of even trying to move it around? Like, I get you saying about resonance, but like, why does it matter?
That's why it matters, because the more resonance forms you can make, the lower the energy is going to be of that system. It's all about sharing those electrons among multiple atoms. The more you can spread the electrons around and the more you can delocalize them, the lower the energy of the system is going to be. And when you're doing chemistry, energy is everything. If you can get from a high energy state to a low energy state, then that's good. That's the goal. All right. So now let's go down here to our reaction. We're gonna actually go through the mechanism of the reaction. So let's look at the molecule here. These are the reactants, NBS. Don't panic about that. That is N-bromo. Let me do something about this. Succinimide. It looks like this. We're going through a lot of hassle to draw this out, but in the end, the role of NBS is just to supply bromine. Right, that supplies bromine. So that's the role of that. The light is ultraviolet, and we need that ultraviolet light to start the initiation process, because that's enough. That's providing enough energy to cause that bond to cleave, right, in NBS and generate that radical. And normally a bromine bond with any atom is weak anyway, because bromine is a really big atom, has a high atomic radius, so it's the bond between bromine and some other atom is going to be pretty long and weak, so it's easy to break. All right, so NBS supplies bromine, the light supplies the energy to start the initiation process. Now, here's the question. For this molecule, where are my allelic sites? Again, allelic means adjacent to an alkene. So where are my allelic sites here?
The CH3.
Good, right here. And where else?
And then the bond right, like to the left of that.
Right here?
Yes, sir.
Yes, that's exactly right. So those are my allelic sites, and that's where the reaction is going to take place. Now, here's the question. Another question. So we got two allelic sites present, so we can fill that in. Right, we can fill that in. Now, the second question asks how many products are possible. Right? We're just predicting at this point. What do you think? If we have two allelic sites and we make two allelic radicals, and you know that the allelic radical can rearrange through resonance, how many products do you think we're going to get total?
4.
4.
Very good. So right now, what we're going to do is go through the mechanism, because see, this is the fourth question, touches on what we've been talking about above with the resonance. It says draw every possible resonance structure for the intermediates formed in propagation. So that's the propagation step, is where all of your rearrangements are going to happen. So I'm gonna add a page instead of trying to squeeze it in. Let me add a page here, and I'm gonna cut this and move it. All right, so I'm going to take this molecule. All right, I'm just going to leave that. So the first step is going to be, and this is, let me write that up here. This is my mechanism. And again, it is a radical mechanism. So it's going to be initiation, followed by propagation, followed by termination. So initiation is going to be taking that MBS, right? And then treating it with light. So I want to break this nitrogen bromine bond. And again, if you notice, all my arrows are fish hooks because it's radical. So that single-headed arrow means that I'm only moving one electron. All right, so I'm going from here to here. Right, so this is bromine is going to be my initiator. Right, and then in the second step in propagation, I'm going to start going, and I'm going to abbreviate this chain because I don't feel like drawing all this stuff out. I'm going to, which side y'all want to do first? Never mind. We'll do the methyl group, the CH3 first. I'm going to put the hydrogens in though that we're going to be dealing with. Right, and the reason these allylic hydrogens are the target is because they're the lowest in energy, right? They're the easiest to remove because you can stabilize them by resonance. I think that was in one of the videos, right? To take off sorry about that. To take off a vinyl hydrogen, one of these, it costs something like what is it? 460 something kilocalories per mole, kilojoules per mole to remove that. But the allylic hydrogens are somewhere in the range of 350 or something like that. So about 100 kilojoules per mole lower in energy. So they're easy to remove, easier. And the reason is because when you pull them off, you can stabilize the intermediate that you get. All right, so that's that plus a bromine radical. All right, so that is going to, let me erase that and fix that up. Let's take this one. That's going to cause, again, homolysis, homolytically cleave that. And then now these two right here are going to end up together on the other side. That's what that arrow means. When those two arrows are coming together like that, right? So we're going to have HBr as a side product. And then we're going to have this radical. Everybody following that? If not, say something.
Yes, I'm following.
All right. So that's the first radical that I make in propagation. And then the other one, I'm going to attack the other allylic site. All right, so I'm going to attack this site right here. One of those. All right, so I'm gonna, I'll just redraw it instead of trying to copy it. Let's see. All right, so that plus BR. And I'm going to cleave this bond. I'm gonna put this electron here, one here, and then one here. All right. So that means I'm taking off a hydrogen, abstracting a hydrogen with bromine. So I'm going to get as one of my side products, HBr. And then my radical is going to look like, and keep in mind, I am abbreviating this, by the way. I'm not drawing out the whole chain. All right. So my radical is going to look like this. That's that. Still have a hydrogen here with one electron. Everybody okay with that?
Yes. Is the bottom CH3 or CH2?
It's CH3. You mean in the second step, propagation step?
Yes.
Yeah, it's CH3. I'm only gonna abstract from one side or the other. I'm not gonna do them both at the same time.
Okay.
Yeah, good question.
Can you zoom out a little bit more? Or like, what were the first two, I guess, reactions? Okay.
So for at the bottom where you have these two different reactions going on next to propagation, it's either one or the other is what you're really saying.
Yeah, but I'm making both. I'm not making them. Well, I could make them at the same time, because if you think about on a molecular level, you got Avogadro's number of, molecules floating around. But yeah, I'm showing it stepwise to show that these are the two radicals that I'm going to get, because both of those are my Allelic sites, and both of those are where the bromine is going to abstract from. So technically, they can happen at the same time, just not on the same molecule. So I'm not going to abstract from the CH3 and then come back and take the radical that I get from that and abstract again from the top CH2. You follow what I'm saying?
Kind of.
It's either going to be one site or the other site, but it's not going to happen within the same molecule.
So you're saying it would take another like reaction to do another breakdown?
Yes.
Okay.
It'll take another molecule of this alkene for another abstraction to happen at the other site. Like, let me see if I can clarify that. I'm not going to take this and do another propagation step on it at the top site. Right? It's got to be another molecule, a fresh molecule that hasn't been abstracted, where the abstraction can take place at the other site.
Okay, I understand that. Thank you.
All right. So now this is propagation. What now? Each one of these radicals are allelic radicals. Am I right? You can see the pattern right here, just like we saw up top. You got the allelic pattern. You got a radical adjacent to an alkene. So what does that mean?
That you can do resonance.
You can do resonance on both of them. Right? So for this one, how would I illustrate resonance? What would I show?
Double-headed arrow.
A double-headed arrow to move the electrons.
I mean, one arrow.
Okay, a single-headed arrow. Where am I gonna put it?
From the double bond to the one to the
Like
right.
that?
Yes.
And it's important. That's really important to show where the electrons are ending up, because I can't just draw the arrow out in space somewhere, because that's not the case. You have to end the arrow where you want it, where you want that electron to be. So if I want the electron to be on that CH2, that's where the arrow needs to stop on that carbon. By the same token, if I want to show that I'm making a pi bond, both of these arrows right here, they need to be, you know, between the two carbons, between the carbon of the alkene and the radical carbon. Like where I place the end of the arrow actually matters, right? So up here, now here I am going to cheat. I'm going to try to cheat anyway. I'm going to put my electron out here and then my double bond here. Is that right? Is that what that resonance, those resonance arrows will indicate?
Yes, sir.
Like that. So that's one resonance form. Based on this allelic radical right here. We'll call it A. And then we'll call this B. Oh no, let's not do that. I don't want to confuse nobody. We'll call this B. Right? So down here we'll call that C. What would you do to C to show resonance and rearrange it?
From the double bond to the left.
Like that?
Yes.
And then put that put that electron right there.
Yes.
So I'm gonna cheat again. So now I'm gonna have a double bond here and one electron here on this carbon. Are y'all following? So now I got 4 radicals that I've created. I made 2 and I got 2 resonance forms, right? So these are all because of resonance. All right, so I made 2 through the traditional way of abstraction, and then I got 2 more because of resonance. So in the termination step, what am I going to be terminating? Let's go back up to the very top when we first start talking about this, right? Do you see how did I show the termination? Yeah. You see how in the termination step, that's when my products come together, right? So I have a bromine radical and I'm reacting with a methyl radical, and then I get the product, which is right here. So what am I going to show in the termination step here? How many radicals am I taking into termination?
Is it 4?
All of them. All right. Yes. So 4. I'm taking all 4 radicals that I made in propagation, and I'm going to terminate all of them. Oh, I got plenty of room. All right. So I'm gonna cut these out. I don't feel like drawing all this stuff. We're gonna call this one D. Actually, you know what? I am gonna redraw them. So this is 1. This is 1. Everybody agree with that? That's 1. And then this is one of the resonance ones. Yeah. And then this is also a resonance. Is that right? This is A. And then this would be, I'll call that one C. This is B. Where's B? B. And then this is D. Yes, no?
Yes.
No, you lost me.
All right, do you see what A is right here?
Yes.
Okay, is this A right here? Where there's a CH2?
Oh, yes. Okay. Okay.
Mm-hmm.
Got it.
Make that a little neater. And then do you see what B is with the resonance form of A?
Now I do. I didn't see it before. Okay. Got it.
And then so that means this is the resonance form of A right here. I just didn't write in the CH2, but I can write it in. And then C is this radical right here. I just didn't write the hydrogen in, but you can see it right there. And I
Yep.
I'll
Got it.
cut down the confusion. And then B is the resonance form of, I'm sorry, is it B? No, D. D is the resonance form for C, right? You see D over here,
Yep.
and then this is D over here. I should have just rearranged it. Let me do that. That's the beauty of using an iPad. I couldn't do this on a whiteboard. We got some new glass, some kind of glass whiteboards now. So it's just like writing on an iPad. All right, so those are my radicals for propagation. All four of them come into termination. And then I'm going to terminate them with bromine
Mm-hmm.
and give my Allelic Bromination products. Again, the goal is to add bromine at the allelic site. Somebody is asking, where's all the bromine coming from? Am I right? I know it's in the back of somebody's mind. Tell the truth, shame the devil. Oh, no, really. If not, that's fine. That's just a common question. But it does have an answer. All right.
So where does brownie come from?
So I knew somebody was thinking that. So up here, when we take MBS and we homolize it, break the bond. Imagine if we take like 1 mole, right? That's Avogadro's number of molecules. So it's like basically an infinite supply of bromine that we're making. Even if we just started with 1 mole of MBS. All right, so you got plenty of bromine floating around. It'll never run out. That's the point. All right, so now I just need to terminate these, and I'm gonna show the first one. All right. So now I'm going to take this radical and this radical. We're going to bring those two together. Let me erase that. All right. So that product is going to look like this, CH2 Br. Anybody disagree with that?
No.
All right. And then the same thing here. We're going to terminate that. The arrow sucks, but sorry. And that's going to be CH2 Br. All right, and then here, same thing. We're gonna show the arrows between those. Oh, sorry. So that's gonna be, put a bromine at that site. And then this is going to terminate here. Like so. All right, any questions about that? So that mechanism is standard. Any allelic bromination is gonna go through this initiation, propagation, and then termination. And if you have, if you form an allelic radical and your alkene is non-symmetrical, like this one, then you're gonna have resonance in that propagation step. So you're gonna end up with more radicals than you started out with. All
Could
right,
you go back to the D?
D, yeah, sure.
Thank you.
And again, the purpose of this is that, again, we're talking about ways of making alkyl halides. And this is one method, allelic bromination. Right, so you take an alkene that has an allelic carbon and you react it with MBS, shine light on it, and you're able to put a bromine at that allelic position. That's important. This is because the allelic bromination product is a precursor, right? You can use it for a lot of other different reactions, right? And we'll talk about we're going to talk about some of the reactions. We're not going to do that Friday because we got to talk about the alcohol stuff, but we'll talk about some of those reactions, in the near future. The main one is using it to make granule reagents or organometallics, and then couple those with other compounds to do synthesis reactions. But we'll talk about that later, probably starting next week. All right, any questions?
I have a question.
Go ahead.
So it's 2 class assignments due, right?
Yeah,
Just the first 2.
yeah.
Okay.
If you after today, when I upload this set of notes, if you download the notes, you'll see exactly what worksheets we're doing. But if you go on Blackboard, the first folder says stereo under assignments. The first folder says stereochemistry. The second one says allelic bromination. So those are the 2 things that we're doing.
Okay. Thank you.
Yep. Other questions?
Also, it was only A through D because when we first started off, it was 2 acrylic points. So that means it was 4 of them. So if there was 4, that would have been 8 different ones.
If there were 4 allelic sites?
Yeah, it would have been 8 different
Yeah.
possibilities.
Yep. That's true. Great question, by the way. All right, other question.
Are you going to do a study session on Thursday?
Yes, that'll be our first one. Yep. I still don't know what's a good time. Like, give me a time, because I really don't know what the best time would be.
Like 7 p.m.
7?
Could we do 7?
Yeah, we can do that. I don't have a life. I'm joking.
Are you gonna record it though?
I will record it. Yep. Speaking of recording, let me stop recording so I don't get all our personal business on YouTube.